Hello and welcome to this introduction video for two brand new model interrogation tools that can be found in SIMCA 16, the Scorespace Explorer and the Multivariate Solver. Both these tools are currently available for regular projects only, but development is ongoing for the extension to batch models. Have you ever wondered why some areas of your score space is not populated? What would a sample look like to correspond to that area in the score space? This is very difficult to answer when you only have to rely on loadings for your interpretation. In SIMCA 16, we are therefore introducing a new tool for generating model understanding called Scorespace Explorer. It works like an inverted what-if or prediction functionality, where you instead of changing the variable settings to see what happens in the model, you interact with your model space to see what happens in your variables. This will give you the variable profile of any fictive point in your score space. For instance, if you're modeling your raw material batches and you find an area in the score space that is empty, you can use the Scorespace Explorer to find out what properties a raw material in this area would have. The Scorespace Exploration tool is found in the new Data Explorer pane, and the pane interface looks a lot like the what if functionality already existing inside SIMCA. But instead of sliders for variables, you now have sliders for the score vectors. And when you start the Scorespace Explorer, you should see two plots. If not, just move one of the score vector sliders in the pane and the plots will appear. To the left in the SIMCA work area, you have a predicted score scatter plot showing the active prediction set. And to the right, you have column plot displaying the variable settings corresponding to the selected point in the score plot. By default, the origin in the scatter plot is selected, indicated by the blue point. The position of the marker can be changed in two ways, either by using the sliders, or you can click directly into the plot and select any point in that scatter plot. You can now directly see and of course also list the corresponding variable profile. And in the case of raw material characterization, you can start creating or looking for a material matching that profile. Another situation where the Scorespace exploration tool is useful is when working with spectral data. You can then use the sliders to understand which part of the spectra is affected when moving in a specific model direction and how sensitive the model is. So if I start moving in the orthogonal direction, I can see that the spectral region around 400 nanometers is increasing. So that leads me to believe that the second component is related to color. If you have a predictive model, a PLS or an OPLS as in this case, you can, together with your input variable profile, also get the predicted output value for any point in the score plot, and thus immediately seeing the outcome of an imaginary point. So if I open up the list, I have the predicted value down in the corner. So whenever I click in this point in the plot, the corresponding predicted value will appear. The second new and innovative tool for converting model knowledge into real-world interpretation is a multivariate solver that works on OPLS models for regular projects. The solver can be used when you know what output you want, but you don't know how to set your input variables, the X block. This is very similar to an optimizer, but the solver is not combining output criteria or automatically finding closest solution. The solver looks for the exact values you're asking for, and you have to control it manually. Let's see how the solver works. Here we have process data from a mineral grinder. Mineral ore comes in and is ground to meet the desired fineness criteria. At the same time, we also keep an eye on the energy consumption per produced unit of the product. So for any given fineness, we want to know what the variable profile looks like that at the same time reduce the energy consumption. First, we fit an OPLS model with energy and fineness as the two Y variables, which are already done here. We then open the solver, which can be found in the Data Explorer pane. And when you start the solver, you should see three different plots. If not, move one of the sliders and they will appear. To the left and right in the SIMCA work area, you have plots that are the same as in the score space exploration tool we just looked at. A score scatter plot of the active prediction set and a column plot of the raw variables corresponding to the selected solution point, the blue point in the left plot. The middle plot is new and displays the y variables. In this case, we have two. To the left, a green and blue bar representing the energy consumption per unit, and to the right, the two bars representing the product fineness. The green bar is the model predicted value, and the blue bar is the requested target value for each y variable. In the solver pane, you have sliders for the two output variables, and this is where we start interacting with the solver. Let's start by deciding on a target fineness. We choose 69. I can use the slider to move until it reaches 69, or I can type in the desired value. We can see that the predictive fineness, the green bar, is exactly the same size as the blue bar for fineness, which means that we're getting exactly what we asked for. Now let's see how low we can go on the energy consumption according to the model. So I start sliding the energy consumption to the left, and we can see the predicted values going down. And we also see the solution moving along a diagonal in the score scatter plot. That is also indicated by some of the gray points, which are the training set observations. When we come to the edge of the model space, the ellipse, the solution point stops. And this is because I'm not allowing the solution to look outside the model region. This is an option that can be controlled in the options menu found in the side pane. Around the energy consumption value about 40, we start seeing that the green and the blue bars separate. But if we move back a little, we see that we should be able to produce this grade at a consumption of less than 41 units, and the variable combination can be seen to the right. Now, of course, a process engineer needs to review this and understand if this is a realistic setting, because there may be other considerations on individual parameters that is not reflected in this solution. This is something we are continuing work on implementing, but until then, we can constrain the proposed solution by entering target values on the X parameters as well. This is very useful if your raw material change and you need to figure out how or if you can compensate with the other process parameters so that you still reach your quality goal. In this example, it may be relevant to see how you can adjust for a specific load of incoming ore. In the solver interface to the right, we can add X variables, and we add ore feed rate and water feed rate. Because I know that these two are highly correlated, so I need to add them both. And then I enter some reasonable settings, 220 and 50. The solver now tells us that we should be able to produce a fineness of 69% and still be below 41 units of energy per produced unit, given this influx of material. Looking at the available historical data, the training data, with a feed rate of 220 and 50, and a fineness measure of 69%, the lowest energy consumption seen was 47 units. But what if we ask for something different? For instance, an increase of the water feed rate to 65. Now the prediction bars turn red, indicating that what we asked for is not available within the model domain. The red color indicates that the probability, P mod X, is too low. We then need to change what we ask for. So let's change the desired value for energy consumption and increase that a little bit. And then it turns green. With these settings on ore and water feed rate, we need to use more than 43 units of energy to produce the correct product quality. And this concludes this introduction to the two new model interrogation tools, the Score Space Explorer and the Multivariate Solver. Hope you find this addition to SIMCA 16 useful, and keep your eyes open for more videos in the feed on the start page of SIMCA, or search for Sartorius Stedium Data Analytics on YouTube. Thanks for watching.